The interface is the air interface for the GSM mobile telephone standard. It is the interface between the mobile station and the base transceiver station. It is called because it is the mobile analog to the U interface of ISDN. Is defined in the GSM 04XX and 05XX series of specifications. Can also support GPRS packet-oriented communication. Layers. The layers of GSM are initially defined in GSM 04.01 Section 7 and roughly follow the OSI model. Is defined in the lower three layers of the model. Physical layer equals. The physical layer is defined in the GSM 05XX series of specifications, with the introduction and overview in GSM 05.01. For most channels, L1 transmits and receives 184-bit control frames or 260-bit vocoder frames over the radio interface in 148-bit bursts with one burst per time slot. There are three sublayers, radio modem. This is the actual radio transceiver, defined largely in GSM 05.04 and 05.05. Multiplexing and timing. GSM uses TDMA to subdivide each radio channel into as many as 16 traffic channels or as many as 64 control channels. The multiplexing patterns are defined in GSM 05.02. Coding. This sublayer is defined on GSM 05.03. On the physical channel has 26 TDMA frames, each frame consisting of 114 info bits each. The length of 26 TDMA frame, also called multi-frame, is 120 milliseconds apart. Radio modem. GSM uses GMSK or 8PSK modulation with 1 bit per symbol, which produces a 13/48 MHz symbol rate and a channel spacing of 200 kHz. Since adjacent channels overlap, the standard does not allow adjacent channels to be used in the same cell. The standard defines several bands ranging from 400 MHz to 1990 MHz. Uplink and downlink bands are generally separated by 45 or 50 MHz and 85 or 90 MHz. Uplink-downlink channel pairs are identified by an index called the ARFCN. Within the BTS, these ARFCNs are given arbitrary carrier indexes COCN1, with CO designated as a beacon channel and always operated at constant power. GSM has physical and logical channels. The logical channel is time multiplexed into 8 time slots, with each time slot lasting for 0.577 milliseconds and having 156.25 symbol periods. These 8 time slots form a frame of 1,250 symbol periods. Channels are defined by the number and position of their corresponding burst period. The capacity associated with a single time slot on a single ARFCN is called a physical channel and referred to as CNTM, where N is a carrier index and M is a time slot index. Each time slot is occupied by a radio burst with a guard interval, 2 payload fields, tail bits, and a midamble. The lengths of these fields vary with the burst type, but the total burst length is 156.25 symbol periods. The most commonly used burst is the normal burst. The fields of the NBR, midamble, a 26-bit training sequence that helps in multipath equalization at the center of the burst, stealing bits, each side of the midamble, used to distinguish control and traffic payloads. Payload, 257-bit fields, symmetric about the burst, tail bits, 3-bit field, at each end of the burst, guard period, 8.25 symbols at the end of the burst. There are several other burst formats, though. Bursts that require higher processing gain for signal acquisition have longer midambles. The random access burst has an extended guard period to allow it to be transmitted within complete timing acquisition. Burst formats are described in GSM 05.02 Section 5.2. Multiplexing and timing. Each physical channel is time multiplexed into multiple logical channels according to the rules of GSM 05.02. One logical channel constitutes of 8 burst periods, which is called a frame. Traffic channel multiplexing follows a 26-frame cycle called a multiframe. Control channels follow a 51-frame multiframe cycle. The COTO physical channel carries the SCH, which encodes the timing state of the BTS to facilitate synchronization to the TDMA pattern. GSM timing is driven by the serving BTS through the SCH and FCCH. All clocks in the handset, including the symbol clock and local oscillator, are slave to signals received from the BTS, as described in GSM 05.10. BTSs in the GSM network can be asynchronous and all timing requirements in the GSM standard can be derived from a stratum 30CXO. Coding: the coding sublayer provides forward error correction. As a general rule, each GSM channel uses a block parity code, a rate 1/2, fourth-order convolutional code and a 4-burst or 8-burst interleaver. Notable exceptions are the synchronization channel and random access channel that use single-burst transmissions and thus have no interleavers. For speech channels, vocoder bits are sorted into importance classes with different degrees of encoding protection applied to each class. Both 260-bit vocoder frames and 184-bit L2 control frames are coded into 456-bit L1 frames. On channels with 4-burst interleaving, these 456 bits are interleaved into 4 radio bursts with 114 payload bits per burst. On channels with 8-burst interleaving, these 456 bits are interleaved over 8 radio bursts so that each radio burst carries 57 bits from the current L1 frame and 57 bits from the previous L1 frame. Interleaving algorithms for the most common traffic and control channels are described in GSM 05.03 sections 3.1.3, 3.2.3 and 4.1.4. Data link layer equals, the data link layer, LAPDM, is defined in GSM 04.05 and 04.06. LAPDM is the mobile analog to ISDN's LAPD. Network layer equals, the network layer is defined in GSM 04.07 and 04.08 and has 3 sublayers. A subscriber terminal must establish a connection in each sublayer before accessing the next higher sublayer. Radio resource. This sublayer manages the assignment and release of logical channels on the radio link. It is normally terminated in the BSC. Mobility management. This sublayer authenticates users and tracks their movements from cell to cell. It is normally terminated in the VLR or HLR. Call control. This sublayer connects telephone calls and is taken directly from ITU-TQ 931. GSM 04.08 Annex E provides a table of corresponding paragraphs in GSM 04.08 and ITU-TQ 931 along with a summary of differences between the two. The CC sublayer is terminated in the MSC. The access order is AR, CC. The release order is the reverse of that. Note that none of these sublayers terminate in the BTS itself. The standard GSM BTS operates only in layers 1 and 2. Logical channels. Logical channel types are outlined in GSM 04.03. Broadly speaking, non-GPRS logical channels fall into 3 categories: traffic channels, dedicated control channels and non-dedicated control channels. Traffic channels equals, these point-to-point channels correspond to the ISDN B channel and are referred to as BM channels. Traffic channels use 8-burst, break, diagonal interleaving with a new block starting on every 4th burst and any given burst containing bits from 2 different traffic frames. This interleaving pattern makes the TCH robust against single-burst fade since the loss of a single burst destroys only 1/8 of the frame's channel bits. The coding of a traffic channel is dependent on the traffic or vocoder type employed, with most coders capable of overcoming single-burst losses. All traffic channels use a 26 multiframe TDMA structure. Full-rate channels. A GSM full-rate channel uses 24 frames out of a 26 multiframe. The channel bit rate of a full-rate GSM channel is 22.7 kbits. Although the actual payload data rate is 9.6-14 kbits, depending on the channel coding. This channel is normally used with a GSM 06.10 full rate, GSM 06.60 enhanced full rate or GSM 06.90 adaptive multi-rate speech codec. It can also be used for fax and circuit switch data. Half-rate channels. A GSM half-rate channel uses 12 frames out of a 26 multiframe. The channel bit rate of a half-rate GSM channel is 11.4 kbits, although the actual data capacity is 4.8-7 kbits, depending on the channel coding. This channel is normally used with a GSM 06.20 half-rate or GSM 06.90 adaptive multi-rate speech codec. Dedicated control channels. These point-to-point channels correspond to the ISDN D channel and are referred to as DM channels. Standalone dedicated control channel. The SDCCH is used for most short transactions, including initial call setup step, registration and SMS transfer. It has a payload data rate of 0.8 kbits. Up to 8 SDCCHs can be time multiplexed onto a single physical channel. The SDCCH uses 4 burst block interleaving in a 51 multiframe. Fast associated control channel. The FACCH is always paired with a traffic channel. The FACCH is a blank and burst channel that operates by stealing bursts from its associated traffic channel. Bursts that carry FACCH data are distinguished from traffic bursts by stealing bits at each end of the midamble. The FACCH is used for in-call signaling, including call disconnect, handover and the later stages of call setup. It has a payload data rate of 9.2 kbits when paired with a full-rate channel and 4.6 kbits when paired with a half-rate channel. The FACCH uses the same interleaving and multi-frame structure as its host TCH. Slow associated control channel. Every SDCCH or FACCH also has an associated SACCH. Its normal function is to carry system information messages 5 and 6 on the downlink, carry receiver measurement reports on the upper link and to perform closed-loop power and timing control. Closed-loop timing and power control are performed with a physical header at the start of each L1 frame. This 16-bit physical header carries actual power and timing advanced settings in the upper link and ordered power and timing values in the downlink. The SACCH can also be used for in-call delivery of SMS. It has a payload data rate of 0.2-0.4 kbits, depending on the channel with which it is associated. The SACCH uses 4 burst block interleaving and the same multiframe type as its host TCH or SDCCH. Common control channels. These are unicast and broadcast channels that do not have analogs in ISDN. These channels are used almost exclusively for radio resource management. The AGCH and RACH together form the medium access mechanism for Broadcast control channel. The BCCH carries a repeating pattern of system information messages that describe the identity, configuration and available features of the BTS. BCCH brings the measurement reports. It bring the information about LAI and CGI. BCCH frequency are fixed in BTS. Synchronization channel. The SCH transmits a base station identity code and the current value of the TDMA clock. SCH repeats on every 1st, 11th, 21st, 31st and 41st frames of the 51-frame multiframe. So there are 5 SCH frames in a 51-frame multiframe. Frequency correction channel. The FCCH generates a tone on the radio channel that is used by the mobile station to discipline its local oscillator. FCCH will repeat on every 0th, 10th, 20th, 30th and 40th frames of the 51-frame multiframe. So there are 5 FCCH frames in a 51-frame multiframe. Paging channel. The PCH carries service notifications to specific mobiles sent by the network. A mobile station that is camped to a BTS monitors the PCH for these notifications sent by the network. Access grant channel. The AGCH carries BTS responses to channel requests sent by mobile stations via the random access channel. Random access channel. The RACH is the upper link counterpart to the AGCH. The RACH is a shared channel on which the mobile stations transmit random access bursts to request channel assignments from the BTS. Allowed channel combinations. The multiplexing rules of GSM 5.02 allow only certain combinations of logical channels to share a physical channel. The allowed combinations for single-slot systems are listed in GSM 5.02 section 6.4.1. Additionally, only certain of these combinations are allowed on certain time slots or carriers, and only certain sets of combinations can coexist in a given BTS. These restrictions are intended to exclude nonsensical BTS configurations and are described in GSM 5.02 section 6.5. The most common combinations are, combination I, TCHF plus FACCHF plus SACCH. This combination is used for full-rate traffic. It can be used anywhere but COTO. Combination 2, TCHH plus FACCHH plus SACCH. This combination is used for half-rate traffic when only one channel is needed. It can be used anywhere but COTO. Combination 3, 2 TCHH plus 2 FACCHH plus 2 SACCH. This combination is used for half-rate traffic. It can be used anywhere but COTO. Combination 4, FCCH plus SCH plus BCCH plus CCCH. This is the standard COTO combination for medium and large cells. It can be used only on COTO. Combination V, FCCH plus SCH plus BCCH plus CCCH plus 4SDCCH plus 2SACCH. 5x1, plus opening round bracket 5 times 1 closing round bracket plus opening round bracket 1 times 4, plus opening round bracket 3 times 4 closing round bracket plus opening round bracket 4 times 4, plus opening round bracket 2 times 4 closing round bracket plus 1 idle equals 51 frame multiframe. This is the typical COTO combination for small cells, which allows the BTS to trade unnecessary CCCH capacity for a pool of 4 SDCCHs. It can be used only on COTO. Combination 6, BCCH plus CCCH. This combination is used to provide additional CCCH capacity in large cells. It can be used on COT2, COT4 or COT6. Combination 7, 8 SDCCH plus 4 SACCH. 8x4, plus opening round bracket 4 times 4 closing round bracket plus 3 idle equals 51 frame multiframe. This combination is used to provide additional SDCCH capacity in medium and large cells. It can be used anywhere but COTO. Fundamental transactions. Basic speech service in GSM requires 5 transactions: radio channel establishment, location update, mobile originating call establishment, mobile terminating call establishment and call clearing. All of these transactions are described in GSM 4.08 sections 3 to 7. Radio channel establishment equals, unlike ISDN's U-channel, channels are not hardwired, so the interface requires a mechanism for establishing and assigning a dedicated channel prior to any other transaction. The radio resource establishment procedure is defined in GSM 4.08 section 3.3, and this is the basic medium access procedure for This procedure uses the CCCH as a uniquest downlink and the RACH as a shared uplink. In the simplest form, the steps of the transaction are: paging. The network sends a paging request message over the PCH, using the subscriber's IMSI or TMSI as an address. GSM does not allow paging by IMEI. This paging step occurs only for a transaction initiated by the network. Random access. The mobile station sends a burst on the RACH. This burst encodes an 8-bit transaction tag and the BSIC of the serving BTS. A variable number of most significant bits in the tag encode the reason for the access request, with the remaining bits chosen randomly. In L3, this tag is presented as the error channel request message. The mobile also records the TDMA clock state at the time the RACH burst is transmitted. In cases where the transaction is initiated by the miss, this is first step. Assignment. On the AGCH, the network sends the RR immediate assignment message for a dedicated channel, usually an SDCCH. This message is addressed to the miss by inclusion of the 8-bit tag from the corresponding RACH burst and a timestamp indicating the TDMA clock state when the RACH burst was received. If no dedicated channel is available for assignment, the BTS can instead respond with the RR immediate assignment reject message, which is similarly addressed and contains a hold-off time for the next access attempt. Emergency callers receiving the reject message are not subject to the hold-off and may retry immediately. Retry. If the RACH burst of Step 2 is not answered with an assignment or assignment reject in Step 3 within a given timeout period, the handset will repeat Step 2 after a small random delay. This cycle may be repeated 6 to 8 times before the miss aborts the access attempt. Note that there is a small but non-zero probability the two misses send identical RACH bursts at the same time in Step 2. If these RACH bursts arrive at the BTS with comparable power, the resulting sum of radio signals will not be demodulable and both misses will move to Step 4. However, if there is a sufficient difference in power, the BTS will see and answer the more powerful RACH burst. Both misses will receive and respond to the resulting channel assignment in Step 3. To ensure recovery from this condition, uses a contention resolution procedure in L2, described in GSM 04.065.4.1.4 in which the first L3 message frame from the miss, which always contains some form of mobile ID, is echoed back to the miss for verification. Location updating The location updating procedure is defined in GSM 04.08 sections 4.4.1 and 7.3.1. This procedure normally is performed when the miss powers up or enters a new location area but may also be performed at other times as described in the specifications. In its minimal form, the steps of the transaction are, the miss and BTS perform the radio channel establishment procedure. On the newly established dedicated channel, the miss sends the location updating request message containing either an IMSI or TMSI. The message also implies connection establishment in the sublayer. The network verifies the mobile identity in the HLR or VLR and responds with the location updating accept message. The network closes the DM channel by sending the error channel release message. There are many possible elaborations on this transaction, including authentication, ciphering, TMSI assignment, queries for other identity types, location updating reject. Mobile originating call establishment this is the transaction for an outgoing call from the miss, defined in GSM 04.08 sections 5.2.1 and 7.3.2 but taken largely from ISDN Q931. In its simplest form, the steps of the transaction are, the miss initiates the radio channel establishment procedure and is assigned to a decimeter channel, usually an SDCCH. This establishes the connection in the L3 error sublayer. The first message sent on the new DM is the connection mode service request, sent by them as this message contains a subscriber ID and a description of the requested service, in this case MOC. The network verifies the subscriber's provisioning in the HLR and responds with the connection mode service accept message. This establishes the connection in the L3 sublayer. The miss sends the CC setup message, which contains the called party number. Assuming the called party number is valid, network responds with a CC call preceding message. The network sends an error assignment message to move the transaction off of the SDCCH and onto a TCH plus FACCH. Once the miss has acquired the timing on the TCH plus FACCH, it responds on the new FACCH with the RR assignment complete message. From this point on, all control transactions are on the FACCH. When alerting is verified at the called destination, the network sends the CC alerting message. When the called party answers, the network sends the CC connect message. The miss responds with the CC connect acknowledge message. At this point, the call is active. The TCH plus FACCH assignment can occur at any time during the transaction, depending on the configuration of the network. There are three common approaches: early assignment. The network assigns the TCH plus FACCH after sending CC call proceeding and completes call setup on the FACCH. This allows the use of in-band patterns generated by the network. This is the example shown. Late assignment. The network does not assign the TCH plus FACCH until after alerting has started. This forces the MIS itself to generate the patterns locally since the TCH does not yet exist to carry the sound. Very early assignment. The network makes an immediate assignment to the TCH plus FACCH in the initial error establishment and performs the entire transaction on the FACCH. The SDCCH is not used. Because immediate assignment starts the FACCH in a signaling-only mode, the network must send the RI channel mode modify message at some point to enable the TCH part of the channel. Mobile terminating call establishment equals, this is the transaction for an incoming call to the MIS, defined in GSM 04.08 sections 5.2.2 and 7.3.3, but taken largely from ISDN Q931. The network initiates the radio channel establishment procedure and assigns the MIS to a decimeter channel, usually an SDCCH. This establishes the connection in the L3 error sublayer. The MIS sends the first message on the new DM, which is the ARA paging response message. This message contains a mobile identity and also implies a connection attempt in the IM sublayer. The network verifies the subscriber in the HLR and verifies that the MIS was indeed paged for service. The network can initiate authentication and ciphering at this point, but in the simplest case the network can just send the CC setup message to initiate Q931 style call control. The MIS responds with CC call confirmed. The network sends an error assignment message to move the transaction off of the SDCCH and onto a TCH plus FACCH. Once the MIS has acquired the timing on the TCH plus FACCH, it responds on the new FACCH with the RR assignment complete message. From this point on, all control transactions are on the FACCH. The MIS starts alerting and sends the CC alerting message to the network. When the subscriber answers, the MIS sends the CC connect message to the network. The network responds with a CC connect acknowledge message. At this point, the call is active. As in the MOC, the TCH plus FACCH assignment can happen at any time, with the three common techniques being early, late and very early assignment. Call clearing equals, the transaction for clearing a call is defined in GSM 04.08 sections 5.4 and 7.3.4. This transaction is the same whether initiated by the MIS or the network, the only difference being a reversal of roles. This transaction is taken from Q931. Party A sends the CC disconnect message. Party B responds with the CC release message. Party A responds with the CC release complete message. The network releases the ARA connection with the ARA channel release message. This always comes from the network, regardless of which party initiated the clearing procedure. SMS transfer on GSM 04.11 and 03.40 define SMS in 5 layers. L1 is taken from the DM channel type used either SDCCH or SACCH. This layer terminates in the BSC. L2 is normally LAPDM, although GPRS attached devices may use logical link control. In LAPDM SMS uses SAP3. This layer terminates in the BTS. L3, the connection layer, defined in GSM 04.11 section 5. This layer terminates in the MSC. L4, the relay layer, defined in GSM 04.11 section 6. This layer terminates in the MSC. L5, the transfer layer, defined in GSM 03.40. This layer terminates in the SMSC. As a general rule, every message transferred in L(N) requires both a transfer and an acknowledgement on L(N)1. Only L1 L4 are visible on Mobile originated SMS equals, the transaction steps for MOSMS are defined in GSM 04.11 sections 5, 6 and Annex B. In the simplest case, error-free delivery outside of an established call. The transaction sequence is, the miss establishes an SDCCH using the standard error establishment procedure. The miss sends a centimeter service request. The miss initiates multi-frame mode in SAP3 with the normal LAPDM-SABM procedure. The miss sends a CP data message, which carries an RP data message in its RPDU. The network responds with a CPACK message. The network delivers the RPDU to the MSC. The MSC responds with an RPACK message. The network sends a CP data message to the miss, carrying the RPACK payload in its RPDU. The miss responds with a CPACK message. The network releases the SDCCH with the error channel release message. This implies a closure of the IM sublayer and triggers the release of L2 and L1. Mobile terminated SMS . The transaction steps for MT-SMS are defined in GSM 4.11 sections 5, 6 and Annex B. In the simplest case, error-free delivery outside of an established call, the transaction sequence is, the network pages the miss with the standard paging procedure. The miss establishes an SDCCH using the standard error paging response procedure, which implies a CC sublayer connection. The network initiates multi-frame mode in SAP3. The network sends the RP data message as the RPDU and a CP data message. The miss responds with the CPACK message. The miss processes the RPDU. The miss sends a CP data message to the network containing an RPACK message in the RPDU. The network responds with a CPACK message. The network releases the SDCCH with the error channel release message. This implies a closure of the IM sublayer and triggers the release of L2 and L1. Security features. GSM 2.09 defines the following security features on authentication of subscribers by the network, encryption on the channel, anonymization of transactions. Also supports frequency hopping, which is not specifically intended as a security feature but has the practical effect of adding significant complexity to passive interception of the link. Authentication and encryption both rely on a secret key that is unique to the subscriber. Copies of key are held in the SIM and in the Authentication Center, a component of the HLR. Key is never transmitted across An important and well-known shortcoming of GSM security is that it does not provide a means for subscribers to authenticate the network. This oversight allows for false station attacks, such as those implemented in NIMS iCatcher. Authentication of subscribers equals. The authentication procedure is detailed in GSM 4.08 section 4.3.2 and GSM 3.20 section 3.3.1 and summarized here. The network generates a 128-bit random value, RAND. The network sends RAND to the miss in the authentication request message. The miss forms a 32-bit hash value called SRES by encrypting RAND with an algorithm called A3, using key as a key. SRES equals A3, RAND, key. The network performs an identical SRES calculation. The miss sends back its SRES value in the error authentication response message. The network compares its calculated SRES value to the value returned by the miss. If they match, the miss is authenticated. Both the miss and the network also compute a 64-bit ciphering key, KC, from RAND and key using the A8 algorithm. KC equals A8, RAND, key. Both parties save this value for later use when ciphering is enabled. Note that this transaction always occurs in the clear, since the ciphering key is not established until after the transaction is started. Encryption equals, GSM encryption, called ciphering in the specifications, is implemented on the channel bits of the radio bursts, at a very low level in L1, after forward error correction coding is applied. This is another significant security shortcoming in GSM because, the intentional redundancy of the convolutional coder reduces the ISDN distance of the encoded data and, the parity word can be used for verifying correct decryption. A typical GSM transaction also includes LAPDM idle frames and SACCH system information messages at predictable times, affording a known plaintext attack. The Gsm ciphering algorithm is called A5. There are 4 variants of A5 in GSM, only first 3 of which are widely deployed. A5/0 no ciphering at all, A5/1, strong, ciphering, intended for use in North America and Europe, A5/2, weak ciphering, intended for use in other parts of the world, but now deprecated by the GSMA, A5/3, even stronger ciphering with open design. Ciphering is a radio resource function and managed with messages in the radio resource sublayer of L3, but ciphering is tied to authentication because the ciphering key KC is generated in that process. Ciphering is initiated with the error ciphering mode command message, which indicates the A5 variant to be used. The MIS starts ciphering and responds with the error ciphering mode complete message in ciphertext. The network is expected to deny service to any MIS that does not support either A5/1 or A5/2. Support of both A5/1 and A5/2 in the MIS was mandatory in GSM Phase 2 until A5/2 was deprecated by the GSMA in 2006. Anonymization of subscribers equals. The TMSI is a 32-bit temporary mobile subscriber identity that can be used to avoid sending the IMSI in the clear on The TMSI is assigned by the BSC and is only meaningful within specific network. The TMSI is assigned by the network with the TMSI reallocation command, a message that is normally not sent until after ciphering is started, so as to hide the TMSI-IMSI relationship. Once the TMSI is established, it can be used to anonymize future transactions. Note that the subscriber identity must be established before authentication or encryption, so the first transaction in a new network must be initiated by transmitting the IMSI in the clear. See also, OpenBTS, GSM 03.40. Further reading, M. Bumolf, S. Orkhtar. Performance Evaluation of Operational GSM's Air Interface. In Proc. Of Applied Telecommunication Symposium, pages 62 to 65, March 2003, Orlando, Florida, USA. External links, 3GPP, the current standardization body for GSM with free standards available. General Packet Radio Service GPRS, Architecture, Protocols, and Air Interface.